Okay. So yeah, I did post this solution for the one I X'd out just in case you want to see it. It's not that it's crazy, it just doesn't belong in level 2, that's for sure. There's just a lot of products to consider. So that answer key is up. I'll still come up with a time where we can go through some of these problems and the alkene practice problems. I do not have an answer key for the alkene addition problems yet, but I will get to that sometime today or tomorrow. Then I also have the handout that I was telling you that's like an explanation of syn and anti with floral arrangements. So you can kind of look through this. I'll leave it posted and let people take a look at it, and I'll either address it in the next lecture or address it in our little review sessions. But this is basically meant to, like the first floral arrangement here, it's showing you how it's sort of planar. It's showing how you could add flowers, 2 new colored flowers from the same side, top or bottom, both top, both bottom, or from opposite sides. And then you cut the vine in the middle so that you can rotate them, and you'll kind of see how they're different. I was very proud of this little handout. It's a lot of flowers. Yeah, flower power, that's right. So take a look at that, and then if it doesn't help, just ignore it. It's flowers. But if it does, at least with a little explanation, then great. Let's see. So that is... Okay, so that's all the 241 review. And then here's the lecture notes. I've got chapter 8, which is just the remaining few alkene reactions that I said we had to go through. There's 3 of them left, so that won't take too much time, 3 or 4, I think, yeah, 3. And then chapter 9 is going to be our first full chapter. That's going to be reactions of alkynes. So reactions of alkynes, the good news is there's a couple new reactions, and almost every other reaction in that chapter is like what we did with alkenes, because alkynes have 2 double bonds, alkenes have 1. So almost everything alkenes can do, alkynes can do either once or twice of that same reaction. So luckily, a lot of that will be familiar from the alkene chapter. If you look at the summary of reactions, you'll see a whole new list, but a lot of those, like I said, will be really just playing off the alkene chapter. It'll be very similar. And then I have something called a synthesis overview and problem solving strategies. That was a tongue twister. I'm not going to start this today because I've got some practice problems at the bottom that I can immediately see requires a few reactions of alkynes. You can do synthesis problems before the alkyne chapter, but I'll wait till we get through some of the alkyne chapter before I come back to this. But this is basically just helping you understand how to approach a multi-step synthesis problem. So usually, at least when I draw them out, I'll put them in this kind of format where I give you a starting material on the left, and then I do a double arrow. That's not meant to say it takes 2 steps, or it just meant to say it takes more than 1 step. And then I want you to try and make the final product. So that could be, like I said, any number of steps. So I want to go through sort of the strategy and the thought process that's required to solve a synthesis problem. And that I think that will be a lot of fun. You guys sound pretty excited about it, which is great. There we go. Okay, so let's finish the alkene chapter. So I think before we finish, because the last few reactions have to do with oxidation, I want to talk a little bit about how you interpret oxidation reduction reaction in organic chemistry. So if you were in general chemistry, you would see something like iron 3+ on the reactant side and iron 2+ on the product side. And what would that be, an oxidation or reduction? Yeah, I always had to think about it in my head. I'm like, loss of electron gain. Yeah, so you're gaining an electron from iron 3 to iron 2, so that's a reduction reaction. So it's much more straightforward because you see a charge, it changes, and then you count the number of electrons that were either gained or lost, and you can say, okay, that's either oxidation or it's reduction. With organic compounds, we still look at compounds like what we see on this list here. And even without reagents, in fact, I purposely omitted the reagents here. I can tell that the transformation from left to right, I can classify it as either an oxidation or reduction, or neither. There's lots of alkene reactions you went through that are not oxidation or reduction at all. It's only a small subset, but you can answer that even without looking at reagents. So I think it's a lot less obvious looking at this how you would say if this is oxidation or reduction.
Can you just scroll up for a second again?
Oh, yeah, sorry. So that's actually what I'm about to talk about now. It's a little less complicated than reading through this whole thing. But ultimately with organic compounds, since we're looking at a neutral starting material and a neutral product, we're not looking at the full-on gain or loss of electrons and a change of charge. Instead, the way we think about it is a gain or loss of electron density. And that electron density that we're referring to is with respect to carbon. So if any of the carbon atoms in your structure gain electron density versus lose electron density, that's the parallel you draw to redox, like from general chemistry. So now we have to know what exactly is meant by electron density. I'm sure you've heard that a billion times, and then out of context, it's not always clear what it means. But ultimately what it means is what the partial charges are. So if you look, for example, here I have it as a CX bond. So X being chlorine, bromine, iodine, nitrogen, oxygen, basically anything that's more electronegative than carbon. Then what partial charge? And we don't usually draw out a bunch of partial charges on molecules, but we do sometimes look at its dipole and figure out what the partial charges are just for our reference. If you had to give a partial charge to the carbon and the, let's call it a halogen here, which one would get the partial minus? Yeah, the thing that's more electronegative than carbon. So here I have a whole list. It can be halogens, nitrogen, oxygen. So whenever carbon is bonded to something more electronegative than it, then it's getting the partial plus on the carbon, partial minus on the more electronegative atom. So carbon-hydrogen bonds are a little strange because we normally teach that those are completely non-polar, that they're just not polar bonds, but they have a dipole. It's just so low that we don't consider carbon or carbon-hydrogen bonds to be a polar bond. But if you did have to assign a partial charge, carbon is more electronegative than hydrogen. So carbon is the one that would get a partial minus, and hydrogen would be a partial plus. So these partial charges are just coming from looking at this atom, the one it's bonded to, who's more electronegative, that one gets the partial minus, the other one gets the partial plus. Okay, so that means that when you gain in a reaction carbon-hydrogen bonds, then carbon is gaining electron density because now you're putting it in a situation where carbon is partial minus. So carbon is partially, by way of the bond just being, the bonding electrons being a little closer to it, is gaining a little bit of electron density. On the other hand, if you form a new carbon X bond, something more electronegative than carbon, now that carbon is losing electron density because, again, the electrons of the bond are now being pulled away from the carbon. So not as obvious as explicit charges, but we're just looking at those differences in electronegativity. So let's take a look at, let's take a look at the very first reaction here. Is that one oxidation or reduction? So you basically want to count up how many carbon X bonds are gained and how many carbon H bonds are gained or lost. Mm-hmm. Yeah, that's a reduction reaction. So I had a bond between carbon and oxygen, and then that's gone, and it's been replaced by a bond to carbon and hydrogen. So here not only are we losing the carbon X bond, but we're gaining a CH bond, so everything is in the direction of that being a reduction. The next one, now this one, I don't want you to sit there and count up oxygens and bonds and all that stuff when you're doing this unless it's just not obvious. But another way to think about oxidation and reduction when it comes to pi bonds is that when you increase the number of pi bonds, that's oxidation. When you go down in the number of pi bonds, that's reduction. Now, ultimately, it's because if you go down in the number of pi bonds, you're gaining 2 new carbon-hydrogen bonds by getting rid of one of those pi bonds, and on the other hand you would have to get rid of 2 CH bonds to add the pi bond in. But I think it's just a nice easy way to visually look at that and say, okay, I went from carbon-oxygen single bond to carbon-oxygen double bond. That's oxidation. And then if I look at the next one, I'm going from a carbon-carbon double bond to single bond. So now that's the opposite direction as far as pi bonds. That's going to be a reduction. And then this last one's a little tricky. I'm not going to ask questions like this and be really annoying. But if you look at this one, on its face, you might think oxidation because you're gaining an oxygen. But you are also gaining hydrogens here. So this one is neither. And the only reason I have that up there is because there are a lot of reactions in the alkene chapter and alkyne chapter that are not oxidation reduction at all. That's just one subset of reactions. So the ones that I looked at the top are redox reactions, but certainly not everything is, not even close. Okay, so I don't want to spend too much time on that. Let's see how many reactions do we have. Dihydroxylation, epoxides. Where's my ozonolysis? Well, that's weird. I'll add it in. I'm missing an ozonolysis reaction. I'm missing one of 3 reactions that we have to go over. So I've got 2 out of 3. It's great. Okay, so let's look at dihydroxylation. This is, in fact, an oxidation reaction. And what we're doing here is we're adding OH and OH across the double bond. So if you think about all the alkene addition reactions, you're adding 2 groups or 2 atoms across your pi bond. So I always like to think about it in terms of what atoms or groups you're adding. Like HBr, I'm adding hydrogen and bromine. H2SO4 form water, I'm adding H and OH. So for this one, what I'm adding is OH and OH. So those are the 2 groups that are being added. The mechanism, so this is going to be a syn addition. And remember, that means the mechanism occurs in such a way that the groups are added from the same phase. It doesn't always mean that there will be a consequence in the final product.
I can't read what's on top of that.
OSO4, sorry. Well, that's not better. That's very large. OSO4 and then water. Yeah, my O's got a little skinny at the top. So yeah, this mechanism occurs by a syn addition, meaning the 2 hydroxyl groups add to the same face of the planar alkene. But this is a case where we're not actually going to see a consequence of that. Maybe I'll change it so that we do. Yeah, why don't I just change it to this just so you can see that syn addition. So I'm going to use that as the reactant. So I'm going to add OH and OH across the double bond. Here I'll actually be able to see that it's a syn addition. So I'm going to add the OHs pointed in the same direction. Now if you get a syn addition, the 2 groups add from the same face. But an alkene is planar. It has 2 equally approachable faces. So they can both approach at the same face on the top or the bottom, or if you orient your alkene front, back, however you orient the plane of the alkene. So it still has 2 options. And same with anti. If they approach from opposite faces, this one can come top, this one bottom, or this one bottom, this one top. So this one, in theory, we would also draw this, where both OHs came from the front. But I actually don't need that. Anyone want to tell me why? So this is actually a meso compound. There's an internal mirror plane, which means it has chiral centers, but isn't actually a chiral molecule. And when you do draw the enantiomer in the way that you normally would, which is where you switch all the dashes to wedges and all the wedges to dashes, you would get to this, but you could see you could just flip it upside down and it would actually be the same. So a lot of times with syn and anti, you'll still draw 2 products. It's going to be a racemic mixture. But here, this is meso. Okay, so the mechanism, I'm not going to go through much of this mechanism, but I just kind of want to show you why it's syn. You have the osmium tetroxide, which looks like this. And I'm not going to count electrons, but I think there's some lone pairs on osmium. I don't know. It seems like a lot of electrons, but I think it has lone pairs. And ultimately what's going to happen in this mechanism, I'm not even really going to draw an arrow, is it's going to form this sort of ring structure between the 2 pi bonded carbons. That bond is going to start to break and it's going to form bonds to those 2 oxygens on the osmium tetroxide. That's enough of the mechanism to see why this would have to be a syn addition. Both of those oxygens are sort of clamping down on the alkene from that reagent at once. So osmium tetroxide either needs to come from one face or the other face, but both of those oxygens will be delivered to the same side. So obviously there's more to that mechanism, but you don't need to worry about any more than that. Let's see. So one of the next reactions we want to go over, and just so you know, if I just move ahead to chapter 9 just for a second, you'll see at the bottom of the reaction summaries, I have a little yellow highlighted asterisk that says these are reactions you don't need to know arrow pushing for. So these are reactions that you need to know what happens when I mix an alkyne with KMNO4, what that product will be, but I'm never going to ask you for the arrow pushing mechanism for how that reagent actually does that. So you'll see that there are a lot of reactions marked in yellow, probably over half of them. And then the ones that aren't marked in yellow, a lot of these are going to be the ones that are extremely analogous to the reactions of alkenes that you've already been through. So the mechanisms in this chapter are not overwhelming. Okay, let's see. I want to, where is it? You know what? Let's just save epoxides and ozonolysis for next lecture. That way I can just make sure it's all up here and we can wrap this chapter up, which should be lecture 4, Wednesday. So let me add that in and then we'll just tie these up together. Alkynes are going to undergo ozonolysis as well, so that'll mesh with the next chapter, but let's just come back to these and move on to alkynes. Okay, so let's briefly take a look at the structure of alkynes. You probably, for your other chapters, when you started reactions, well, I guess alkenes mainly, you looked at the structure of the alkene in terms of whether it was, tetrahedral, planar, what the arrangement of the atoms were, what the orbitals look like, what the orbital overlap is, because sometimes that'll be relevant to some of the reactions we'll go over. So let's start off by just looking at what an alkyne looks like. So I've got these green arrows coming from that one carbon. What is the geometry about that carbon? Yeah, linear is the exact term, but yeah, it's planar, and more specifically, it's linear. So this bond angle, let's write that in, linear. That means this bond angle is 180 degrees. So when you have longer alkynes, try to make sure, I guess let me draw this slightly differently. Try to make sure you draw this bond out straight. So you don't want to draw your alkyne something like this. Because now it almost looks like it has like cis-trans geometry like an alkene. Now, just drawing an ugly bond angle alone is not something I'm going to penalize you for, but I think it could lead to confusion, which is why you want to probably draw it better with the 180 angles. So yeah, that's one thing actually about alkynes. I don't know why I had to erase that. Is that they're not going to have cis-trans geometry like alkenes did, because alkenes had 2 groups on each side of the pi bond. Alkynes only have 1 group on each side. And they can't possibly be cis-trans because they're both pointed out perfectly linearly. Okay, so what is the hybridization of that carbon? Yes, great, sp. And let's see, what else do I want to talk about? Okay, the orbitals. Let's just take a look at the orbitals. So you might remember that for an alkene, let's take a look at I don't know why that keeps happening. Let's look at the sigma bond first. So when you form a sigma bond between 2 carbon atoms, they're going to overlap. I'm going to draw them off to the side. Here's the sp3 orbital for 1 carbon atom, and I've got it pointed this way. Oh, Christ. And then I've got another one for the other carbon atom. Okay, this is fun. That's supposed to look the same as the other one, but I'm not great at drawing. So this is called a head-to-head overlap. So these look sort of like skewed p orbitals if you stick them upright, But when you form a sigma bond, you want maximal overlap, so they overlap what's called head-to-head. So when you sort of mush these two together, the sigma bond looks like this. And the shading is arbitrary. It's just meant to show that the two overlapping, if they're both shaded, are both in phase. Okay, so that's what the sigma bond looks like. The reason we do the sigma bond with that kind of overlap is because if you look at where I have that shaded pink part, which is where there's the most chance of having electron density, it's right between those two carbon atoms. It doesn't get any more between those two atoms than that space I have drawn right there. And so that's what your sigma bond does, is it wants to put it in the best possible place to share the electrons. Now the pi bonds, they do, oh my God, it's gonna drive me nuts. They do side-by-side overlap. So pi bonds are always made of pure p orbitals. So you're always gonna wanna overlap two p orbitals side by side like this. And that's gonna be what forms the pi bond.
Sorry, can you zoom out super quick?
I can, sorry about that. Good? Yeah. And I'll upload these annotated notes as well. So those blue p orbitals now can overlap. And what you'll notice is if you sort of mush these two together, I'll just draw it combined and then add it to the other drawing. So I'll draw carbon, 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 carbon. And you kind of mush those orbitals together, you essentially get what looks like a hot dog bun. You have electron density on the top and on the bottom, like a bun sandwiching those two carbon atoms. So now I'm just gonna superimpose that onto here. So now when we have the first pi bond, it looks like a little piece of pink candy with a hot dog bun around it. And then when we do the other pi bond, because there's a second one here, we have to use another set of p orbitals, and they can't be the first two. So these I have drawn, py. So I need to now either draw the px or the pz. They have to be 90 degrees. So I'm gonna draw these, forgive my drawing skills, but imagine p orbitals sort of pointed in this planar direction. So if I took the blue ones and just rotated them 90 degrees backwards. When I combine these two, it's gonna look very similar. It's really hard to draw these on top of each other, but I'll just sort of draw it in the background. Basically, imagine the two blue hot dog buns. You take another hot dog bun and you sandwich the front and the back of the hot dog instead of the top and the bottom. So now you just have the two sets of buns surrounding that. So that's where all the electrons fit in. And again, you see the sigma bonding electrons are the ones that are most squarely between the two carbon atoms. The pi bonds are in the general space between them, the next best option, but we can't have them overlap with the sigma electrons. Okay, that was fun. People love orbitals, I know. I actually really love orbitals, but I might be alone there. Okay, there's two types of alkynes. This might seem like an arbitrary classification, but it is important. Sorry, I hope it's still recording. I don't see that icon. We'll see. There's internal alkynes and terminal alkynes. So this is internal. And this one is terminal. Again, it might seem arbitrary right now, but there is an important reason why we classify them that way. So internal simply means that both sides of the carbon-carbon triple bond have a bond to carbon. So if I look at the internal, I look at the two carbon-carbon triple bond, alkyne carbons, and then I look at what they're attached to. Here's a carbon. I don't care how long the chain is, how short it is. If it's attached to that carbon, then that's all I care about. And over here, also attached to a carbon. So that's why this one is called internal. And terminal is pretty simple. The alkyne is just on the end. So that means you're just looking for an alkyne that's on the end, and one of the alkyne carbons then would be bonded to a hydrogen rather than a carbon. So here's a terminal one. It's bonded to carbon on one side, but on the other side, it's bonded to hydrogen. You could also have one that's a very specific alkene, acetylene, just bonded to two hydrogens. I suppose that would sort of be considered terminal. God, that's a hideous drawing. So that's acetylene. You could consider that terminal as well, but most terminals we'll look at are something like the one I have drawn. So the big difference between internal and terminal alkynes has to do with an acid-base reaction. Anyone, did you guys learn pKa's? Did you put them on like your note cards or have to, anyone remember the pKa of an alkyne hydrogen? I'd be so amazed. Guess? Ooh, that's wildly acidic.
30.
Close, a little lower.
28.
Oh, just the first part of that. 20, yeah. Yeah. So the pKa of wait, is it 20? Yeah, because it means they're 35. Yeah. The pKa is around 20. Why do I feel like I'm off on that? Either way, that's a close enough estimate. If you compare that pKa to really any other carbon-hydrogen bond, you can't really deprotonate any other carbon-hydrogen bond. You can never pull a hydrogen off just an alkane carbon. Like if you have something like this, there's no base that exists that will simply pull that hydrogen off and give you an anion as a result. It doesn't mean there aren't reactions where you can remove that hydrogen with other things happening, but you are not going to be able to do an acid base where you simply pluck that off and form a carbanion. And that's because if you look at your pKa table, the strongest base on your entire list, or the weakest acid, is a carbon-hydrogen bond, an sp3 carbon-hydrogen bond. So you basically, if that's the strongest base that exists on your pKa table, what's the base that's gonna be able to form that? There is no such base. So there are ways to form anions, but through a usually free radical reaction, so you don't need to worry about that. So these pKa's of alkanes are around 50. That's just not even remotely acidic. That's as least acidic as you could possibly get. If you look at alkenes, the pKa of any of these hydrogens is around 45. So that's basically not acidic at all either. But when you go down to the alkynes, now you drop down to a much lower pKa. I probably have I don't know why that pKa is driving me nuts. I feel like I'm a little off on it. Oh well, still makes the point. Gosh, I haven't done pKa's in a while. So that's relatively acidic. I mean, it's not acidic in the sense that like, oh, you're gonna spill it on your arm and it's gonna eat your flesh off. It's like not that acidic at all. But was that too graphic an example?
No.
It's to me like if I even spill acetic acid on myself, I'm going to be washing that off pretty quickly. Now my alkynes might be toxic for other reasons, but as far as an acid goes, I'm not going to be worried about its corrosive properties. But with a pKa of 20, it is something you can definitely deprotonate. So one of the really common bases you would use to deprotonate is anything with a nitrogen with a minus charge. I'll have more examples down here. I'm shoving it up here just to make the point while we're up here. Those two hydrogens could be alkyl groups. They could really be anything, but that's going to be the classic base that we use to deprotonate an alkyne. And that's because I think they're 25 alkynes.
It up, it says 25.
Ah, finally, I got it. Glad I said it before you told me. So 25, so let's just look at an alkyne. Actually, I have it right here. I don't know why I'm redrawing it. Let's look at a specific acid-base reaction with an alkyne. So I said usually the base we use is going to be a negatively charged nitrogen. There are other bases, but this is just the standard base. So I'll just use NH2-. You could see this as NaNH2. And then, of course, if there's alkyl groups on the nitrogen, that's fine too, as long as it's a nitrogen with a minus charge. So when I have this base, the lone pair is going to come in. Always with an acid-base reaction, you're starting on a lone pair on the base, landing on a hydrogen. And now I'm going to break that carbon-hydrogen bond, land the electrons on carbon. So we have not yet seen anything quite like that. We've not landed a negatively charged lone pair on a carbon atom before. And that's because it's not stable outside of an alkyne. And then the other product would be NH3 neutral. and then I'm showing another reaction after that, but let's just look at the acid-base part for right now. Let's take a look at that. Did you learn how to do like equilibrium constants for acid-base reactions? Does it sound familiar? Where you look at the pK of the product side and the reactant side. Yeah, so it's basically just a way of telling you if a reaction is favorable, an acid-base reaction. So the acid on the reactant side, which is this side, what's acting as the acid here? Exactly. Yeah, even if you just look at the arrow push in, like that's the one that loses a hydrogen, so the alkyne. So this is my acid. And then on the product side, what is your conjugate acid, right? So you're always going to have acid base, and then product side, conjugate acid, conjugate base. So I'm just looking at an acid on each side. It's just a shortcut for determining which side is favored. What is the conjugate acid on the product side over here? Yeah, NH3. So let's look at the pKa's of those two. Once you identify the acid on each side, this pKa is 25, which after much internal struggle came about. And then pK of neutral nitrogen, anyone remember that? Huh. Anyone want to venture a guess? Did I hear 35? That's excellent. Who remembered that? Oh, wow, a lot of hands popping up suddenly. I like it. So that's a pK of 35. So without calculating an equilibrium constant, which you can do here, you can just do 10 to the power of the product pKa minus the react. You don't need to really do that. Just look at the side where the pKa is higher. A higher pKa means what for an acid? Strong or weak? Weak. If you form a strong acid versus a weak, which one is going to be more favorable energetically for a reaction? What does it want to form? Weak, more stable products, exactly. So if you just look at the pK on the reactant side and the pK on the product side, whichever side has a higher pKa is the side that's favored. That's going to be a reaction that will be favorable if it's on the product side. So here, 35 versus 25, 35 is larger, so that is a very sufficient base to deprotonate an alkyne. If it was the opposite, you would basically have in your reaction flask just the acid and base sitting there without really any product forming. Are we close to time or something? No. Why did I got the feeling people were trying to pack up or something. Sorry. So let's see. So that is the typical base we're going to use. That, for one, is the reason that we distinguish between terminal alkynes and internal. For one, we're going to want to utilize this acid-base reaction for an incredibly important function in just about a minute here. But the other thing is that this acid-base reaction has a potential to occur. So let's say I want to do a reaction on this alkyne, and I don't want to take advantage of this acid-base reaction. I want to do some other totally different reaction, but it happens to involve a base. Well, you better check if that base is strong enough to deprotonate the alkyne and whether that's going to interfere with your reaction. So that's a little more abstract until you see examples, but that's basically two reasons we want to be aware of terminal alkynes. For one, we're going to be able to do this awesome reaction that I'm about to go over. And for two, you want to make sure that some other base that is unintentional isn't interfering with whatever reaction you want to do. Okay, so up until now, important question for you. This is organic chemistry, carbons, carbon structures, carbon-based structures, reactions. What reaction have you learned where you form a new carbon-carbon bond? Certainly we must have learned some because this is organic chemistry, carbon-based structures. So what reaction have you learned before now where you form a new bond between two carbons? Yeah? But what do you add in addition? You add hydrogen, hydrogen, hydrogen and chlorine, hydrogen and oxygen, oxygen and oxygen. So if you look at all the addition reactions, the things you add are hydrogens, oxygens, chlorines, whatever. You don't actually form the new bond between carbons. Yeah? What's that? Oh, you can, but in the context you learned them, you just added halogens, although there were some where it like formed weird carbon structures. But so not reliably in that way, but I like that popped in your head. Yeah?
Elimination reactions, forming new double
Okay, that's a loophole. I like it. That's good. That's good. So you do form a new carbon-carbon pi bond. That's absolutely correct. But the initial two carbons were bonded already. You just now added a pi bond. But that's a great response. It's true, but we added a new carbon-carbon pi bond.
I feel like you're tricking us.
I am tricking
Okay.
you. All this time, a full semester of organic chemistry, you haven't learned to make a single carbon-carbon bond?
Ring expansions.
You got me there. You got me there. Okay. Yeah. You exchange one carbon-carbon bond for another, but that is forming a new carbon-carbon bond. I'll give you that. So yeah, I mean, it's in a sense, it's kind of wild that all this time, a full half of organic chemistry is over, and you don't know how to make a carbon-carbon bond, and you don't know how to break one. Spoiler alert: you haven't learned how to break one either. Ozonolysis is going to be your first example of that. That's the one I'm going to come back to. But even more exciting is forming a new carbon-carbon bond.
Oh my god.
Right? I mean, mind-blowing. So that is the other important part of this acid-base reaction, is let's take a look at what we form as the product. And let me just sort of redraw this. Why don't I draw this a little bit more neatly down here? I'm just going to recreate this reaction. An H2 minus. I'm going to leave out the arrow pushing down here just to simplify it. So if you're looking at the alkyne carbon, now that we've deprotonated, it's got a negative charge. Would you say that that is more likely to act as a nucleophile or an electrophile? Yeah, negatively charged lone pair, that sounds like a nucleophile or a base. We're going to look at it in the context of a nucleophile, but we do want to consider it as a base as well. If you look at any other carbon species, it was always categorized, on carbon anyway, as an electrophile. So an alkyl halide, that carbon attached to the halogen is electrophilic because of the partial plus charge. What other electrophiles? I guess if you protonate an oxygen, you make it leave, but ultimately everything you've looked at in terms of the reactivity at carbon, nucleophile versus electrophile, it was always electrophile. Now we have the complementary thing. We have carbon that's a nucleophile. Carbon nucleophile, carbon electrophile, carbon-carbon bond. I'm just going to stand up here and creepily look at you until you show me the same excitement. So the reaction that we'll do here is actually the electrophiles that you're used to seeing, which are alkyl halides. We will learn other electrophiles that can react here, but for now it'll just be alkyl halides. So if I draw an alkyl halide like this, what kind of reaction is this? I have a nucleophile that's negatively charged. Yeah. Yeah, it's an SN2. So I have a negatively charged nucleophile that's strong. And then I have an alkyl halide primary. This is going to be an SN2 reaction. So it's in a slightly different context, but ultimately this step right here is SN2. So I'll do the arrows for this. The lone pair is going to come into the carbon. Maybe I'll draw it around this way. It's going to hit that carbon atom. And then we're going to kick off chlorine as the leaving group. Now let's number these. Because people often, very often, lose carbons or accidentally add too many carbons in these reactions. So I usually number the entire alkyne piece, and then I number the alkyl halide piece. So for continuity, I would give, since I went 1, 2, 3, 4, 5, I would give carbon number 6 to the carbon that 5 is actually reacting with, which is the one attached to the chlorine. It doesn't matter if you number it differently, but I think it makes more sense to then call this 6, and then what's attached to 6 is 7 and 8. So 6 is the thing that's going to accept that pair of electrons and form the new bond, but 7 and 8 are, of course, are still going to be tagging along because they're attached to 6. So the product, and you know what it is? I think it's the linear bond angles that is the cause for people gaining or losing carbons when they draw out the product of this reaction. In fact, I do it all the time until I number it. 1, 2, 3, 4, 5, and then 6, 7, 8. You'll often find that you're missing one or you have too many, and you can just adjust it by the numbering.
Isn't there like when it's SN2, isn't there like in yours, or should it be like if it,
So SN2 does give inversion of configuration. So if you have an alkyl halide, that's the electrophile. When the nucleophile comes in, it does backside attack on the electrophilic carbon. So that carbon, if it's chiral, is when you'll see inversion. So mechanistically, this still does backside attack and does geometrically an inversion, but if there's no chiral center.
I didn't notice it's 8.
Oh, I'm sorry, what?
It's 8 carbons.
Yeah, exactly, yeah. Mechanistically, it does still do inversion, but there's no structural consequence to that. Okay, any questions about this reaction so far? So this, let me draw this out more in the way that you would typically see it. Okay, I'm just gonna draw it off to the side here. You would draw an alkyne. I'll just draw R, the hydrogen. And instead of drawing out the base in one step and then an anion and then the alkyl halide in a separate step and then that product, when we have to do things in 2 steps, meaning first we have to add the base and form the nucleophile from the alkyne. Then once we have a nucleophile, then we can toss in the alkyl halide. We'll usually give it Roman numerals. This isn't like a formal rule, but I usually use lowercase Roman numerals to show that it's not 2 reactions, it's just a 2-step reaction. It just means everything's in a flask, I add the base, I wait a few minutes, then I toss in the alkyl halide, I get a product. So it's still really one reaction, but you're adding reagents in separate steps.
So would the deprotonated alkyne be sterically hindered at all? Because it seems like it's a straight line.
Exactly, it's actually very sterically unhindered.
So could you do this on like a tertiary carbon?
No, but I'm glad you brought that up because right here you'll see this reaction in pink, I wrote all over it now, is limited to primary alkyl halides, and then the question is why. So sterically, yes, it seems like you might be able to get away with doing an SN2 on a secondary. Tertiary is basically they're never going to do SN2, so no matter how sterically unhindered a nucleophile is, it's just never happening. But secondaries are the one that are at least possible, but they can be a stretch. And if something's super unhindered, a lot of times you can get SN2. This one's tricky. We didn't really look at this in the scope of like strong nucleophiles versus bases when we thought about substitution and elimination, or I assume you all didn't either if it's taught similarly. But the issue here is that the alkyne carbon, when it's an anion, is pretty strong base. So this is a back and forth between being pretty sterically unhindered, but also being a very strong base. The fact that it's very strong as a base makes it more likely to give you E2. So in the end, ultimately, you have to do primary alkyl halides. Secondary alkyl halides will do an E2 elimination with that alkyne anion, and tertiaries will as well. And that's a very fancy waste of time way to do an E2 reaction, because you can just take your alkyl halide and add sodium hydroxide and call it a day. So you wouldn't want to do this on a secondary or tertiary because that would be a very weird way to do an elimination reaction. It wouldn't give you the new bond. So let me go back up here. Of course, I'm running out of space. Oh, you got enough room over here. I'll add it in. And then you draw your alkyl halide, so I'll give this an R prime. Just different from R.
Oh,
Yeah.
Okay.
Maybe R1, R2 is easier. And then the final product. So just so you see the way we would normally format that as a whole reaction, I wanted to break it down into 2 steps. And this overall reaction, I know the explanation that made the notes a little bit messy here, but this overall reaction is in the summary of reactions at the bottom, so you can very clearly see the way all these are set up. In fact, I'll just whip down there for a minute. yeah, you can see it right here. It's got numbers. It shows you the way that that reaction is formatted. Okay, let's see where we're at here. Okay, so these two reactions are the way that we make alkynes. I see that I only have about a minute left, so let me summarize what's happening here, and then we'll finish it next time. Ultimately, you'll see both of these starting materials have 2 halogens on them. You know that you can do an elimination reaction with an alkyl halide to form an alkene. Stands to reason that if you have 2 halogens properly situated relative to one another, you could do a second 2 eliminations back to back, and that would give you a carbon-carbon triple bond. So these both are basically going by a double E2 elimination to give us the alkyne. And then the good news is all of these are just alkene reactions that can happen either once or twice on an alkyne. That's ultimately pretty much the rest of the chapter. Huh? Yeah, that's what I was saying. It comes up with alkynes as well. Yeah.
I was like, you're looking for it. I was like,
I'll probably just start there with those remaining 2 reactions next time so they don't get lost. And I'm like, what? I never went over them? Okay. I've got office hours right after if anyone has questions.